Hi. So we're going to be talking about two things today. And the first is programs that look for bugs in the glue code between C++ and JavaScript. And that glue code is called binding code. And second, we found a lot of binding errors happen for the same reasons again and again. So we made a new binding layer API that prevents these errors by construction. But before I can talk about that, I have to talk a little bit about binding code and, as a consequence, about JavaScript. So okay, let's say we have a JavaScript interpreter. It implements the JavaScript language. And we're trying to write a piece of JS that connects to the network. But we're sort of stuck in interpreter land, right? So we need to somehow be able to reach outside of that in order to establish this connection. And that's where binding code comes in. It's written in a lower level language, like C or C++, so it can open a network socket in the usual way. But we're able to call it directly from JavaScript via a normal JavaScript function call. And so that allows us to do everything from open up this network connection to open a file to invoke a function in a shared library. And in fact, binding code is really pervasive because it's necessary. We need it any time we have to reach outside of interpreter world. And so JavaScript engines, the pieces of code that run JavaScript, provide APIs that allow us to write our own binding code and extend the JavaScript environment however we want. So this is what binding code looks like at a high level. We have a JavaScript application at the top, and it's able to call into the C++ binding layer. And that binding code uses a JavaScript engine like V8 to manipulate JavaScript values or expose whole functions back to JavaScript. So let's say we want to write a string to a file, but we want to do that from JavaScript, and again, we're stuck in interpreter land, can't do it. But luckily, we can from C++. We have this write file function, and it writes a string to a file, just as you'd expect. And conceptually, what we want to do is turn that into a function that accepts JavaScript arguments instead. So we're going to write some binding code. And this binding code can accept JavaScript arguments using V8's general JavaScript argument type. And then it's going to convert these arguments to C++ strings using the asString function. This also comes with V8. Then we have these normal C++ strings, string and file name, and we can call write file as normal. So you can sort of think of binding code as JavaScript written with C++ APIs, right? Because it has to manipulate these JavaScript values. So we have our write file function, but we still can't get to it from JavaScript. We have to expose it to the JavaScript layer. And that's a matter of just making one more function call, again using V8, and now our function is exposed to JavaScript. We can call it just like a normal JavaScript function. And this works with the file system, but it also works in the browser. We need it in the browser. If we want to move a page element, if we want to connect to a server, all of this is going to require binding code. So in the browser, what that means is we have our web page JavaScript that's talking to our browser C++ bindings, and that's on top of the browser JavaScript runtime. So okay, now we can work with JavaScript with the file system and in the browser. This is all great, but of course, as always, there is a problem. And that is that binding code reintroduces whole classes of errors that the JavaScript language should prevent by construction. So for example, JavaScript is a crash-safe language. All errors should manifest as catchable exceptions, right? So JavaScript will not hard crash. But of course, we know C++ is happy to hard crash all the time. So these C++ bindings can reintroduce hard crashes to the JavaScript language. And at a high level, this is how this is going to work. So if I'm an evil ad developer, and I'm able to identify a line of code in those C++ bindings in the browser, if I can figure out how to trigger that from JavaScript, I've introduced a hard crash from JavaScript. And remember that this is possible because binding code can accept user JavaScript arguments. So okay, we've identified our bug, we're able to hit it from JavaScript, and now we've reintroduced the crash to JavaScript. And this doesn't just work with normal C++ errors like segfaults. Binding code, since it has to manipulate JavaScript objects, actually has many more ways of going wrong and crashing. And so this evil ad has all sorts of opportunities to just crash your tab. It doesn't just happen with crash safety either. Bindings are able to violate all sorts of JavaScript's fundamental safety guarantees. So JavaScript is a memory-safe language. For example, you shouldn't be able to touch uninitialized memory. C++ is not at all. You can have a use after free bug, you can have out-of-bounds reads or writes, and if we can find some way of triggering those from JavaScript, we've reintroduced memory errors to JavaScript, and this can allow us to do all sorts of bad things like read sensitive data. Similarly, JavaScript has some notion of type safety, and we can violate that using bugs in the binding layer. What this means is that bindings, to be secure, must actually preserve all of JavaScript's guarantees, but in C++. So that can boil down to essentially writing perfectly memory-safe C++ code all the time. And if that were really easy, maybe we wouldn't need a higher-level language like JavaScript anyway. So what we want to do is help binding layer developers by finding and preventing bugs in JavaScript bindings in 4 different runtime systems: the Chrome extension system, Blink Chrome's rendering engine, PDFium, and Node. This talk, I'm going to condense it just down to 2. Node, which is a platform that allows you to run JavaScript outside of the browser, so maybe on the command line or on the server side. And PDFium, which is Chrome's in-browser PDF rendering engine. And remember that PDFs have to be able to embed JavaScript. So PDFium must run JavaScript, but it also extends the JavaScript environment with new PDF-related APIs. So that can get a bit complicated. All right, so we created some static checkers that find bugs in JavaScript bindings in these 4 systems. And these static checkers examine code looking for buggy patterns. And that's in contrast, say, to tools that run code in order to find bugs. Here's the general pipeline of a static checker. We're going to parse a binding layer function, get back some program representation. Our checkers are going to attach to that representation and report back bugs. Our checkers are system-specific as opposed to language-specific. So a language-specific static checker, for example, will look for null pointer dereferences in all C source code. It works on all source code in the language. These checkers only work on PDFium or Node, and they look for patterns that we've identified in binding code that lead to violations of JavaScript safety. We wrote checkers for 5 different kinds of bugs, and we validated these bugs by writing 81 proof-of-concept exploits. So most of these were for hard crashes in Node, but some of them were for more serious, like memory-related errors in PDFium. Now, what do these bugs look like? So this is a buggy binding layer function, and before I can talk about how it's broken, I'm going to talk a little bit about what it does. So this fill function efficiently fills in a buffer from a start index to an end index. And since it's exposed binding code, we can call it from JavaScript. So we can say fill, and this will fill in our JavaScript buffer from index 0 to index 5. First, this fill function is going to do a little bounds checking in JavaScript, and then it's going to call into the bindings. And the bindings are going to retrieve the uint32 value of the start index, and then the uint32 value of the end index using the V8 API. Then it's going to memcopy based on these indices to fill in that buffer. Oh, there we go, there's memcopy. So let's think about how this can go wrong. We need to choose some, or want to choose, some from value and some to value, such that we pass this JavaScript bounds check here, but we're still able to get malicious values here so we can write outside of the bounds of the buffer. To do that, we got to look at uint32 value, this function. So this is a V8 function, and if you call it on a number, it will just return that number back to you. If you call it on an object, though, it does something called implicitly casting. And so normally, it's just going to throw you back 0 and say, OK, I'm going to cast your object to 0. That's its number value. Unless in JavaScript, you define this toPrimitive function. And the toPrimitive function tells V8 how to implicitly cast this object. So if you have toPrimitive return 3, uint32 value is going to return 3. Similar with 5, or you can make it return something different every time. And that's what we're going to do. So the first time toPrimitive is called in this JavaScript bounds check, we're going to return a good value. We're going to return something in the bounds of the buffer. The second time it's called down here, though, we're going to return an evil value, something that's outside of the bounds of the buffer, so that we can control the start location of that write of that mem copy. And we found this bug using a checker that looked for any place where user JavaScript can affect a memory operation like memcopy or malloc. And this checker walks through source code, keeping track of two pieces of information. It keeps track of unchecked types, which are all incoming arguments that have not yet been explicitly type checked in the binding layer. Then it keeps track of something called dangerous values, and that's a little complicated, but it's looking for cases where implicitly casting functions, like uint32, are called on variables that have not been type checked, that are in that unchecked type set. Anytime that's assigned to a variable, that variable goes into dangerous values. This becomes a little more clear when we walk through it. So first, args is the argument to fill, so we're going to add it to unchecked types because it hasn't yet been explicitly type checked. When we get down here, we see that uint32, an implicitly casting function, has been called on argset2, and argset2 has not been type checked, right? So this could potentially call back into user JavaScript, allowing user JavaScript to affect the value of start. So we're going to add start to dangerous values. Same thing with end, and then because start shows up in this memcopy and in dangerous values, we're going to flag a bug. And this checker, I think, found 5 memory errors in Node and 1 false positive. So here's one more bug that we found. This is a use after free in PDFium, and this function is just supposed to rename an annotation in a PDF. So VP is our user JavaScript new annotation name, and BA_annot just represents the annotation field in the PDF. This line here is the problem. It's supposed to be assigning VP to be the new annotation name, but PDFium has overridden that write shifty operator to be an assignment operator and to call into V8 functions that upcall into user JavaScript. So this line here upcalls into user JavaScript. And in user JavaScript, we can remove that annotation field. Just get rid of it from the PDF, force garbage collection, and then on this line here, BA_annot no longer exists because it was garbage collected during that upcall. So this previous bug and another one were bountied, so that's a sign that system authors are taking these bugs at least somewhat seriously. Other high-level checker results, we found 81 confirmed bugs. This is the breakdown. We can crash most of PDFium's external APIs and the most node modules, like exposed functions. And all of our node crashing exploits work on Node Chakra Core, which is a node version that uses a different JavaScript engine, not V8. So that's a sign that people are misusing different JavaScript engines in very predictable ways every time. So now that we've talked about some bugs, we can talk about how to prevent them. We want an API that forces developers to handle JavaScript-related errors at the binding layer. So we won't have any JavaScript-related hard crashes. And that should preserve JavaScript's crash safety. We want the API to insert type checking for the developer so they don't have to explicitly type check in the binding code. And this should help preserve JavaScript's type safety. Finally, we want to make it really clear when functions can upcall into user JavaScript. So remember that uint32 value function? It was not clear at all, really, that that could call back into JavaScript. Nothing about the name or how it's used suggested that. So we want to make it really clear when functions can do that to try and help developers write more memory-safe code. So this is our rewrite of the fill function, that buffer fill function from before. I'm not going to walk through how we did it, but I'm just throwing this up here to show you that we were hoping to make C++ that looked a little more like JavaScript, since what we're essentially doing is writing JavaScript with C++ APIs. We implemented the API as a backwards compatible wrapper for V8. And we tested backwards compatibility using Node's own version-to-version regression testing. So that's 1,000 tests, and then the test suites of 74 popular NPM modules or packages. We found a worst-case overhead of about 11%, but the average was pretty negligible. And to test performance in a real-world setting, we grabbed a popular Node package, ran its performance tests, and then ran that with our new rewritten Node with our new API. and we found about 1% overhead, so nothing disastrous. All right, so this is just the wrap-up. We wrote static checkers. They found 81 exploitable bugs in binding code. They're system-specific, so they're for the systems that we check and for binding code specifically. And then we wrote an API that prevents these bugs by construction. It's backwards compatible, and it has pretty negligible overhead. So if you have any questions, I'd be happy to take them now. Thanks so much.
I'm Richard Novgalwa. So as far as I understand, your checker uses manually hard-coded patterns on the AST?
Yeah, so we looked at a lot of binding code and then figured out how it was going wrong with these upcalls. And we figured out a few patterns, and then we checked the AST. We basically are just doing pattern matching on the AST.
And about how many patterns was it?
I think it was like 5 checkers, but about 7 patterns, because we have to change the patterns per system, because system idioms get kind of weird.
Okay, and how do you know the patterns are exhaustive?
Oh, they're not. Yeah, also the checking system we're using is like totally unsound. So we're making no guarantees about finding all the bugs in the systems.
Okay, thank you. Second question. So I imagine like a different solution for the API problem where you could instead write sort of a wrapper in JavaScript that would coerce all your arguments to the types that you expect. And have you explored that direction?
We haven't explored a JavaScript solution to the question. We've mostly been working from the binding layer.
Okay, thank you.
Thanks.
All right, so I have a question.
Sure.
The simpler API that you guys proposed looks very, very convincing to me. And I'm curious to see whether it would be possible to formally specify for the new API that you propose some correctness guarantee that it will prevent hard crashes, and try to prove that about just the implementation of that API form, perhaps because it might be a small enough piece of code to do that on. Have you considered this?
Yeah, that's actually something we really want to do.
So future work then. Well, let's thank, one more question
one
here.
more?
Very good talk. So have you ever used the client static analyzer?
Oh, yeah.
Yeah, they provide a static analyzer engine, and you can also customize the checkers on top of it. Have you ever compared that tool with your static analyzer to check the binding?
So you could, assuming you can compile these bindings with Clang, you can write our checkers in Clang too and just run that.
Oh, okay.
Yeah.
Yeah, thank you.
Thanks so much.
All right, let's thank the speaker.